Okay, so in this part of this short video, I will talk about the fracture mechanics. Uh, well, we will not go into much details about this topic, just to mention very some important aspects. So first of all, fracture mechanics is a very detailed field. It is actually a separate subject. So some branches of the engineering, this is a course which is taught. So one of the principle which is applicable for the material science is that it is related with the failure of the material, and failure results from the fracture in the material, and the fracture in the material results from, that means it starts from the cracks. Once the crack is produced or it's present in the material, then that crack propagates due to the effect of the external forces as well. The second point which is important in this uh, part is that the when we measure the strength of most of the materials, this measured strength is uh, always lower than the one which is predicted by the theory, or the by the equations, theoretical equations. So this is due to the presence of the microscopic flaws in the form of cracks, which always exist in the materials. And we also know that there are some uh, dislocations and vacancies which we already have discussed, which we already have learned in the previous lesson. So these cracks and flaws exist, so therefore the major fracture strength of most materials is much lower than the predicted strength. Uh, and one What is then the effect of these cracks? The effect of these cracks is that at the tip of the crack, since the cracks are normally quite sharp at their tips, the area uh, of that tip area for the application of the force at that point at the tip of the cracks is much smaller. So due to this very small area, the stress at that point gets amplified. Okay, so the stress, because as we know that the stress is equal to force divided by the area, but when the area is very small, then the stress would increase, so stress is amplified. Due to that amplified stress at that point, the crack then starts propagating, and then uh, uh, when the propagation of the crack is to some certain extent, then the failure in the material takes place. So this can be shown by this diagram. As you can see that there is this one material specimen. Uh, this material specimen is subjected to the tensile stresses, and in this material specimen the some of the cracks have been shown. So this is the internal crack over here, and this is over here, this is the external crack over here. So if you take the width of this external crack, or the length of this external crack, equal to A, and the length length of the this internal crack we can take as 2A, because for the external crack it is a kind of one half of the internal crack. So for the consideration of our, and for the uh, development of some equation, so we consider the length A equal to the one the length A equal to the length of the external crack, which is one half of the length of the internal crack. So this is the magnification of this part over here. The This part is is kind of like a circular arc. Since this is a circular arc, that circular arc will have some area. That area is represented by this symbol rho subscript t, rho t. When we use these values over here, then we can develop this equation. Of course, the development of this equation is not included. It is not in the scope of this course. So more detailed, proper fracture mechanics studies would deal with the derivation of this equation. So we get this equation, which is sigma m is equal to 2 sigma naught a over rho t. So sigma m is the stress at the tip of the crack. Okay, stress at the tip of the crack, and sigma naught is the normal applied stress, and a is, I already explained that the a is the length of the external crack, and rho t is the area of the crack tip. So we have this equation, so we can use this equation for our numerical problems. Next, we can discuss about this slide. This slide shows the variation of the stress. Okay, so for example, if you have this crack, internal crack, the stress at this internal crack is equal to sigma m, and then that stress then gradually decreases at the surface, okay, at the surface of the body to sigma naught. So there is a variation of the stress. So the highest level of the stress is at the crack tip, okay, and then which reduces to the normal stress sigma naught at the surface. So in this way we can take a ratio of this sigma m and sigma naught as well, and then that ratio is called as the stress concentration factor. So stress concentration factor is basically the ratio of sigma m and sigma naught. As we can see over here, if you take sigma naught from this side of the equation to here, so that remaining value is 2 the bracket a over rho t power 1 by 2. That is the ratio sigma m over sigma naught. Sigma m over sigma naught, we define it as stress concentration factor. Okay. Next, there is some explanation about the crack propagation. So how we can apply this crack propagation concept for the brittle and the ductile materials. Okay, so for the brittle materials, you can see that if this is the crack, since the material is brittle, so material has no plastic deformation. So whenever there will be a stress on the crack tip, there will be no, since there will be no plastic deformation, there will be no increase in the area or in the curvature of the crack tip. So therefore the crack will very quickly propagate in the brittle material. But in the case of the ductile material, there will be a plastic deformation, so the crack area, the area at the crack tip will increase, in the radius of curvature for the crack tip would also be greater in the case of the ductile material. So if I go back to this equation over here, so radius of the curvature for the crack tip will be greater for the ductile material. So therefore there will be a lower amount of this stress which is at the crack tip. So the stress will reduce at the crack tip for the ductile material, but for the brittle material, there will be higher amounts of stresses over here. Okay, next is so next we have this equation. Okay, so again the derivation of this equation is not included, which is out of the scope of this course. Well, this equation is about the stress and with the subscript of C. So stress with this subscript of C, it means it is the critical stress for the crack propagation. So over here, this equation over here, this is actually a kind of an induced stress as a result of this applied stress. So if this induced stress is greater than the critical stress, then the crack will propagate. So the equation over here is about the stress capacity. Okay, stress capacity. So this is related with the modulus of elasticity of the material and a quantity which is called as the specific surface energy, which is represented by gamma s over here. And again, it is related with A. So in this equation, if you see over here, uh, model of elasticity we already know. The specific surface energy is not very well explained in the book, but actually it is, you can understand it to be like the energy needed at these an energy needed to remove the surface atoms, okay, per square meter. It's kind of this kind of thing. So because it is represented in terms of the joules per square meter, so you can consider it to be like the energy needed to remove uh, atoms from the surface of the material. Okay, so this is the specific surface energy. A is the 1/2 of the length of the internal crack, as we already know. So as if in this case, if you see that if A is greater, the length of the crack is greater, the critical stress, that is the stress capacity, will reduce. Okay, so a shorter crack length is needed for higher capacity, and then higher is the modulus of elasticity, more is the stress capacity, and similarly for a specific surface energy. So let's see this the use of these previous equations, rather this equation in this example. So in this example, if you see that a relatively large plate of glass is subjected to a tensile stress of 40 megapascal, if the specific surface energy and modulus of elasticity of this glass are 0.3 joule per square meter and 69 gigapascal respectively, determine the maximum length of a surface flaw that is possible without fracture. So in this case, if you see that if I apply this equation, the values of E and gamma S have been given, the stress value has been also given. We have been asked to find the let me see. So we have been asked to determine the maximum length of the surface flaw that is possible. So we need to find the value of A. So it is a simple, straightforward question. So for example, 69 gigapascal is the value of E, 0.3 joule per square meter is the value of the gamma S, and 40 megapascal is the value of the stress, okay, which is which will be used over here. So that means if 40 megapascal is the maximum stress, so we can input these values in this equation, and then this is the solution. Okay, so you can rearrange this equation. Okay, we can rearrange this equation to make it like A is equal to 2e sigma 2e gamma s over pi a square. Just simply input these values, and then you can get a value equal to 8.2 micrometer, or you can convert it into millimeters as well. So this will be the answer. Okay, so that's all for this video clip. So we will continue this topic in the next video clip.